Dynamic programming is proposed. It is a method of breaking a problem into reasonably sized subproblems and using these partial results to compute the final answer. Dynamic programming technique is a recursive programming technique. New algorithmic improvements as well as increasing computer capacity make it possible to align a query sequence against a large database in a few minutes. S. Needleman and C. Wunsch were the first to apply dynamic programming approach to the problem of sequence alignment in 1970. The idea of dynamic programming is described here. We have two sequences X and sequence Y. Suppose there is n characters for sequence X and m characters for sequence Y. Then construct a matrix F with n plus 1 rows and m plus 1 columns. F of ij will be the score of the best alignment for the sequence X and sequence Y in different positions varying from 1 to I for sequence X and from 1 to j for sequence Y. F of ij will be the score for the best alignment in different cells of the characters of sequence X and sequence Y in the matrix. We call each cell in the matrix as the locations ij. F of ij is the value for the cells in the matrix. We will discuss how we can fill the value of f of ij, that is score of best alignment, soon in this class. Now consider the example. The two sequences given are AGC and AAAC. So the n character sequence X is taken as AAC and m character sequence Y is taken as AGC. Sequence X has 4 characters AAAC. So n plus 1 rows are made for the matrix as shown in this figure. So with 4 characters AAAC, 5 rows are created in the matrix. M character sequence Y is AGC consists of 3 characters. So number of columns with this matrix will be m plus 1, that is 3 plus 1. 4 columns will be formed as shown in the figure. Now we have to check the possibilities of alignments between the sequence AGC and AAAC, and we have to write the best alignment score for the different possibilities in each of these cells. And finally Fij, the best score of alignment is taken. We had mentioned that one way to specify dynamic programming is using the recurrence method. Here we will find the Fij score for one cell with different combinations, and recursively the same process will be done for the remaining cells in the same way. Now we are trying to compute the Fij value in a cell, that is, we are trying to find the score of the alignment of two sequences for the position characters of I and j in each cell. we choose the possibility which has the highest score. The highest score is computed by Needleman Wunsch algorithm as f of ij is equal to maximum of f of I minus 1 comma j minus 1 plus s of xi yi, or f of I minus 1 comma j plus gap value, or f of I comma j minus 1 plus gap values. The first case, that is matching xi and yj sequence, is checked by f of I minus 1 j minus 1 plus s of xi yi. That is, we take the value from the diagonal element above and to the left, that is 1 1, and add the match bonus or mismatch penalty for the two nucleotides along the axis, representing an alignment of the two nucleotides. To understand clearly, let us consider this example. We are trying to consider the cell f of ij as f of 2 2, that is second row second column position. First we take the f of I minus 1 f of j minus 1 cell position, that is diagonal value, that is 0. Then add the match bonus or mismatch penalty for the two nucleotides along the axis. On both axes, the nucleotide on second position is A on X sequence and Y sequence. So there is a match. In this global alignment example, we assume match score is +1, mismatch score as -1, and penalty for an alignment with a gap is -2. Since there is a matching case here, we add the diagonal element 0 with matching score value +1, and thus the cell value becomes +1. But we cannot assure now whether this is the maximum score or not. For that, we have to check the other two possibilities, that is f of I minus 1 comma j and f of I comma j minus 1. To consider the score of f of I minus 1 comma j for the position second row second column, f of I minus 1 comma j value is f of 1 comma 2. That is, we can take the value from the above 1 2 and add the gap penalty. Thus f of 1 2 value -2 is added with the gap value -2 is equal to -4 will be the second possible cell value. Third possibility is we can take the value from the left, that is 2 1 position, and we have to add the gap penalty. That is f of I comma j minus 1 plus g is equal to f of 2 1. That is, we can take the value from left, -2 plus gap value, that is -2. Now, as Needleman Wunsch algorithm says, we have to take the maximum of these three possibilities. Now, the three possibilities are: through diagonal, the value score is 1. From top, the score is -4. From left, the score is -4. So the highest score, the maximum score, is diagonal value, that is 0 plus 1, that is +1. So we fill f of 2 2 with +1. Except the first row and first column of this table of matrix, all other cells are filled using this formula using this method of Needleman Wunsch algorithm. That is, we take the maximum value of these three choices. The first row and first column of the matrix is filled through the initialization process, as we do not have the previous rows and columns, and we do not have previous diagonal elements. So while initializing, the first row and column of the table are initialized with multiples of gap penalty as shown in this figure. Here the gap penalty value is -2 in our example problem. So we are taking the multiple of -2. Once we have filled the position 2, 2, we can fill in the rest of the row 2 in a similar manner as discussed as per the algorithm, then followed by row 3, and likewise for the rest of the table. That is, we fill the rest of the matrix from top to bottom and left to right for each f of ij. To understand, consider one more position 2, 3 in the table. The three choices for filling in this position are: first, we can take the value from the diagonal element above and to the left, that is the value -2, and add the match bonus or mismatch penalty for the two nucleotides along the axis. Here the nucleotide values along the axis for the position 2, 3 is A and G, so it is mismatch. So we are adding the penalty value -1 along with the diagonal value -2. Thus diagonal score is -3. Now we are taking the value from above, that is 2, 3 position is filling using the top position 1, 3, that is value -4, plus the gap value -2, that is from top the value we received is -6. Then we take the value from the left +1 and the gap penalty value -2, and score is -1. Now, as per Needleman-Wunsch algorithm, we have to take the maximum of these three values. From diagonally, the value that we have received is -3. From top, the value is -6. From left, the value is -1. So the highest maximum score is from left. So we take the left value -1 for the cell 2, 3, 3, 3. Similarly, we fill all the cell position in the table. Once the table has been completed, the value in the lower right represents the score for the optimal gapped alignment between the two sequences. So in this example, the lower right position value is -1. That is, f of m plus 1 n plus 1 holds the optimal alignment score. So in this global alignment example, the optimal alignment score is -1. Now we have found the optimal alignment score. Now, to recover the alignment sequences in the exact way, we have to trace the pointer back from f of m plus 1 n plus 1 position to f of 0, 0 to recover the alignment. Now, to reconstruct the alignment from the scores table, we need to find a path from the lower rightmost entry in the table to the upper leftmost position. To form this path, we can move from our current position in the table to any other position that could legally have produced the score in the current position. To get an idea about the path, we write the arrow mark for the legally produced score as shown in this figure with sketch pencil. Now, to convert a path to an alignment, we simply recall our original interpretation of the partial scores array. A vertical move represents a gap in the sequence along the top axis. A horizontal move represents a gap in the sequence along the left axis, and a diagonal move represents an alignment of the nucleotide from each sequence at the current position. For example, consider the path highlighted in this figure with green color. Using these moves arrows, we reconstruct the alignment backwards from right to left. The first arrow is diagonal, so we align the last two nucleotides C and C. Next arrow is vertical, so there is a gap in the sequence along the top axis, that is y-axis. Next element is diagonal. Next arrow is diagonal. So we take G in y-axis and the corresponding A from x-axis. Last arrow mark is also diagonal. So we take the nucleotide value A and A from x and y axis, and thus one optimal alignment can be attained as sequence X A A C and sequence Y as A G gap C. By following all the paths in the partial score table, we can reconstruct all possible optimal alignments between the two sequences. Recall, we have three possibilities for each position: a gap in the first sequence, a gap in the second sequence, or an alignment of the nucleotide from each sequence, that is, no gap.